Hi, my name is Marcel Aach, and I'm a PhD student at the University of Iceland and the Jülich Supercomputing Center, which hosts one of the largest supercomputers in Europe. My presentation is on the topic of optimal resource allocation for early stopping-based neural architecture search methods. The motivation for this paper comes from the field of high-performance computing, where usually lots of parallel compute resources are available, which means that you can run neural architecture search with a large degree of parallelism. So in general, you would allocate one worker, where a worker these days is in most cases a GPU, to each architecture candidate and run the evaluations in parallel. This motivates the first research question we seek to answer, which is how many GPUs should I allocate in total for a NAS optimization run to not waste resources? The second research question is motivated by the fact that the evaluations of the architectures could also be split up among multiple GPUs themselves with data parallel training of the networks. So the question is not only how many GPUs should I allocate in total, but also how many of those should I allocate for each trial. If your total number of GPUs remains fixed, which is usually the case in high-performance computing, you need to trade off between allocating resources to enforce NAS parallelism on the left side here, which means that there are more trials running in parallel, and allocating resources to enforce trial parallelism on the right side here, which means that the trials themselves are running faster. To investigate this, we use 4 early stopping algorithms that are Hyperband, Aach, and Bob. They all follow the principle of terminating trials that do not show good performance early on. And as a baseline, we also train with random search. For consistency reasons, we use the RayTune library to compute these evaluations. The benchmark we use to get comparable results is the NUTS bench library, where we use a fixed convolutional neural network topology, varying just the number of channels in each stage of the model. The search space therefore consists of the number of channels, which is varied between 8 and 64. And because the neural network has 5 stages, that means there are roughly 32,000 possible architectures here. Other hyperparameters, such as the learning rate or the weight decay, are kept constant here. The datasets supported by this benchmark are all from the computer vision domain, namely Cypher10, Cypher100, and ImageNet 16120, which is a downsampled version of ImageNet with just 120 classes. The supercomputers we ran these experiments on are located here in Jülich and in Barcelona, featuring machines with NVIDIA A100 GPUs, the older generation V100, as well as the AMD MI50 GPUs. Regarding the first research question of how many GPUs it makes sense to allocate in total, the metric to look at from an HPC point of view is the scalability, which is computed by taking the runtime a program takes for running on 1 GPU and divided by the runtime it takes to run on G number of GPUs. To get a more comparable metric, often the parallel efficiency is computed, which is the scalability divided by the number of GPUs. This value is bounded by 0 and 1, where larger means better. The results here show that a random search has by far the best efficiency, which is also expected as it has only minimal communication requirements, while the early stopping-based methods all have a pretty similar parallel efficiency curve. We see that if we want to stay above a parallel efficiency of 75%, which is a reasonable thing to do, we should allocate no more than 32 GPUs in total for our NAS optimization run. For the second research question and the trade-off between allocating resources to the NAS loop and the single trials, we first look at the case where the fixed compute budget we have available is a single GPU. RayTune actually makes that possible to run multiple GPUs to run multiple trials on 1 GPU. Here we see that the more we enforce the NAS parallelism, the shorter the overall runtime of the NAS optimization loop is. The This becomes mainly visible when you look at the red and the green lines in the plots here. So these two lines are usually the first one to finish. We also see that the effect on the accuracy is rather small, usually less than a percentage point here. Now switching to multiple GPUs and running actual data parallel training, we fix the amount of compute resources to 16 GPUs here and use up to 4 GPUs for data parallel training. And here again, we can see that enforcing more NAS parallelism means shorter overall runtime. In this plot that corresponds to the blue line, which means we're using 1 GPU per trial. We see that here, for example, in the case of Bob, when comparing the runtime of the blue line with the one, for example, of the green line, speed up with a factor of 2 is actually possible. So 1 GPU per trial would be the optimal resource allocation here. However, we also see that enforcing more trial parallelism, the green line, means that the trials converge faster in the beginning. So we have a steeper increase here, at least for Aach, hyperband, and random search, for using more GPUs per trial. To rule out effects from the underlying hardware, the previous experiments were all run on A100s. We run the single GPU experiments again on the AMD MI50, and the multi-GPU experiments on the V100s. Here we see again that the higher degree of parallelism and the NAS loop, the shorter the runtime. So in the left plot, this is the case for the red or the green line here, while in the right plot, this is the case for the blue line. The last point, we increase the amount of total compute resources even further to 64 GPUs and rerun the experiments for Aach with ImageNet 16. Again, here it is visible that the blue line, which corresponds to having 1 GPU per trial, has the shortest runtime. And when we compare that to using a large number, 16 GPUs for data parallel training, we see that we get a speed up by a factor of roughly 5 here, which is quite substantial. So to summarize our main takeaways, we've seen that allocating resources in such a way that more trials can run in parallel is favorable over allocating more resources to the single trials so they can run faster. By following this recommendation, speedups between a factor of 2 to 5 are possible. In total, it seems favorable to allocate not more than 32 GPUs for a NAS run to keep the parallel efficiency above 75%. And as the last point, I want to mention that while these kind of evaluations, of course, consume a lot of compute resources and a lot of energy, they can help us to reduce resource usage in the future. Thank you.